First, thanks, Doug. I liked your presentation. I completely wrote that thing before I saw your presentation, but cool anyway. So now hopefully everyone is kind of caught up with the safe network at a high level and kind of all the different moving parts of it, so we can deep dive into a more specific topic. And that's going to be PARSEC. So PARSEC is our new fancy consensus protocol. It stands for blank. Protocol for asynchronous, reliable, secure, and efficient consensus. Yeah, it's part of routing. I'm a member of the routing team, so I've been designing it, and now we're coding it. So yeah, I'm gonna kind of cover why we needed a consensus protocol, kind of what PARSEC is, where it fits in the network. So hopefully the key takeaway points are that it's actually not rocket science, but you know, it's cool tech. So the way we're going to cover this, we'll start by introducing routing, not even as well as Doug did in his presentation, so that's a bit disappointing. But because PARSEC is kind of a component of routing, so that's going to give you a bit of the context. Then we're going to explain why we ended up needing a consensus protocol and why the existing protocols out there didn't match our needs. And so why we ended up having to invent PARSEC. And then we'll cover kind of at a semi-deep dive, semi-high level, because time is limited, so I can't fully deep dive on everything. But I'm going to deep dive on some things, and hopefully for the rest you can come to a next talk that's going to be more deep dive. And finally, a little slide at the end about what's next, both in the roadmap side of things and kind of upcoming events in London if you're interested. So routing, like Doug told you, it's the brain of the safe network. And when you say brain, what you're also saying is it's not the muscle of the safe network. So basically, there is a ton of things that routing doesn't do. So it doesn't connect nodes together to form a peer-to-peer network, because as Doug said, that's something that's done by crusts. It doesn't authenticate computers that join the network, because that's a cool thing that's done in self-authentication, which is its own library. It doesn't encrypt data. First of all, we don't do our own encryption. We use secure, well-known crypto primitives. But also we have that cool thing of self-encryption, which is encrypting data with its own chunks. And that's also not done by routing. It's all these things you can think of as like the muscle, like the actual things that need to get done for the network, they're all done outside. We're just the brain, so we're just like coordinating different moving pieces. So routing doesn't even handle how data is stored, even though you could think it does. It just assigns nodes, so computers, responsibility to deal with certain types of data. And these nodes are vaults, and they actually do the data handling. Routing doesn't provide an API to write decentralized apps. That's something that Safe Client Lib does, and that's like one layer of abstraction above routing. So that calls into routing, but routing doesn't do this. Okay. And it doesn't conform to semantic web standards. That's the solid integration that we've been speaking about, like with pattern and these kind of things. So all that to say, I could keep going, but you already look pretty bored, so I'll stop here. Yeah, so there are many, many things that routing doesn't do. Just to kind of give, in the big picture, routing is really just a small part of the safe network. And it's got one specific job, which is coordinate computers and data. So if you split that a bit more granularly, the responsibilities, one of the main responsibility of routing is to maintain the network topology. So that's what people call sharding in, say, Ethereum or other cryptocurrencies or whatever. So the idea is to split the network into sections, and like we said earlier, the sections are never overlapping, so each node has a responsibility, and there is no, I don't know, mixing up who should do what. Then routing also assigns a closed group for each piece of data, so that you know which nodes manage the data. And that's independent from maintaining the network topology, which is done by sections. Then routing has the responsibility of mitigating civil attacks. So if you think of Bitcoin, you've probably heard of like the 51% attack, or with the consensus protocol, you've heard of the, I don't know, 33% attack or whatever. So we have things like node aging and secure relocation that, again, Doug brushed on, which allow to add kind of security at every layer of the stack. So the consensus already provides some security guarantees, and then the routing layer provides even more on top of this to prevent civil attacks. So then the other responsibilities of routing are related to moving data across the network or within a section. So this one, allowing secure communication across sections. So the sections are disjoint. So any node is only in one section of the network. And any node within one section doesn't necessarily know about another node in another section. And yet data needs to go from any node to any node, and trust must be maintained. That's something that's done within routing with a mechanism called secure message relay. So if you're on the forum, you can check it out for more details. But basically, that's one of the responsibilities of routing. And then enabling consensus within a section. As you can see, it's kind of like one bullet point amongst many bullet points, just to show the scale. So routing is a small part of the safe network, and then consensus is a small part of routing. And so that's what we're going to speak about today. So now, how does routing solve all these problems? Because it can seem pretty abstract, pretty complicated even. So what we do two things. One, we pretend that everything is a 256-bit integer. So that's what Doug was speaking of, a string, like he meant a string of binary digits. So basically an integer. So first of all, when we say everything, because we've already taken out a lot of the responsibilities away from routing, everything means computers and data, and that's it. All the other layer of abstractions are just handled in different parts of the network. And then 256-bit integer. So an integer is like 0, 1, 2, 3. And 256 bits means that you've got 256 bits to store the integer. So that's pretty large. That allows you to store a number between 0 and this number, which is 2 to the 256 minus 1, or around 10 to the power of 77, or around 0.1% of the atoms in the universe. So the reason we need such a big number is because we want to be able to index any computer in the world and any data on the internet. So that's a pretty big space, and we want to be just sure that we are covering it. So with 256 bits, you know you've got no problem. And what's cool with storing everything or representing everything as an integer is that you can then represent it in binary. So this is just 256 zeros and ones. And that way you can do the kind of math we like, which is simple math. Like, is it true, is it false? So I told you routing does two things. So the first thing is to pretend everything is a 256 integer, and then reduce every problem that I listed in my bullet point list to simple mathematical problems. So I'll give you an example. I'll take one of the points in the list, which was deciding where nodes go in the network. So let's say we've got this node. It's got this ID, 1101. It's a 256-bit integer represented in binary. And I want to put it in a section of the network. So the property I'm looking for is disjoint. So I want for the sections to not be overlapping. I'm not super fussed on having exactly the same size in each section. I want it to be roughly well distributed. And because these nodes are kind of random, say they're the hash of data, they don't have a particular pattern to them, we can do a pretty simple trick. So imagine the network is split into left, right, and then each part is split again into two. So left, right, left, right. And then we've got this node, we want to put it on the network. Well, we can just look at the first digit. It's a 1, it's going to go in the right. It's a convention. 1 right, 0 left. Second digit, it's a 1, it's going to go in the right of the right section. Third digit, it's a 0, it's going to go in the left of the right section. And that's super simple. See, like, so we just express things as integers, and then say, like, you've done 3 levels, maybe now you've got around 100 nodes, which is what you're looking for. So you can just put your node there, you don't have to go deeper. If you have a bigger network, then you can just go 4 levels, 5 levels, exactly what you need. So yeah, like this is an example of how you just completely simplify the problem, it becomes a simple math problem, and then it's trivial. So I'll give you another example of this. So I told you that routing was also responsible for deciding who manages which data. And data, like nodes, has an integer identifier that you can see in binary. So now I've got this binary thing which now represents a piece of data, and I'm asking which nodes should, which vaults should handle this data. Well, the answer to this one is also pretty trivial, but it requires a little bit of prerequisite knowledge. You can just store it in the group size closest nodes in XOR distance. So the property we're looking for here is having an exact number of copies. So like Doug was saying, you want to upload a picture of a cat. If 100,000 people want to upload the same picture of a cat, you still want to store it, let's say, 8 times. So that if any computer fails at any point, you've got time to back it up before it's too late. So this 8, which I just said 8 between quotes, it's group size, some constant. We can see with testing which is the best group size to never lose data and yet not overload the network. So if you pick the group size closest nodes in XOR distance, what you're gaining is that XOR distance is extremely easy to compute. You just look at each binary digit and you do one simple operation. And also it's unique. So if you mapped the computers, for instance, to 2D space, and you said I'm going to put it in the 8 closest computers, then if you had 8, 9, 10, and 11 at the same distance of you, you'd have a problem. But with XOR space, the nice property is that distance is unique, so you don't have this problem. Yeah?
So you touched on this, the backing up that happens. So
yeah.
There's a piece of data, it doesn't really matter how popular it is, it's just a piece of data,
yeah.
And it has this XOR fingerprint of it, which determines where it gets stored on,
yeah.
on the network. So if you've got duplicates of it, 8 of them, wouldn't they all have the same name or the same fingerprint and be stored in the same location?
So the data here is this exact fingerprint. Okay. And then it's the nodes that are close to the data that store the data, and it's the group size nodes. So it's not just one node, it's like, say, the 8 closest nodes to the data. So the data always has one fingerprint, and then vaults know because they're one of the closest to the data, then they're going to store it. Well, and routing organizes that.
Okay, so any member of the network could
yeah.
look at that fingerprint and say, I know for sure, based on certain parameters, that there'll be copies of it stored on these different 8 machines.
Yeah.
And I can find them. Okay.
And that's extremely important because you don't have a central point to contact to ask where is the data. So everyone needs to agree on the rules about where the data is, and once you've done that, you're good. And so I'm going to give you another trivial example of a problem that's solved by routing, like we can go all night. How do members of a section agree on the order in which things happen? So now I have to admit I kind of lied because I said that we simplify everything to simple math problems, but sometimes we can't. So then we try to hit a solved mathematical problem, but then sometimes we can't. And then we try to hit a formulated mathematical problem with some ideas of how to solve it, and this is one of these. So in that case, how do nodes in a section agree on the order in which things happen? It's an expression of the Byzantine generals problem, which is a well-known computer science problem with some solutions that have some properties and not necessarily all the properties we need. So now we're getting into the why we need consensus. So Byzantine generals problem is another word for consensus. We also call it sometimes ABFT, which is asynchronous Byzantine fault tolerant consensus protocol. The problem, why it's called general Byzantine problem, is because it was described in 1982 with a metaphor of Byzantine generals camped around a town that want to attack the town. And you know that in the generals, some of them could be loyal and some of them could be traitors. But if all the loyal generals don't synchronize on their attack, say if only half the loyal generals attack the city, they will definitely lose because there'll be not enough number to take the city. So they can only communicate with each other with messengers, and the messengers can be extremely slow or intercepted, and then some of the Byzantine generals can lie or try to confuse other Byzantine generals. But in the end, you need to make sure that all loyal generals agree about when to attack the city. So it was expressed like this with a metaphor because Leslie Lamport thought that it would have more traction that way, and it actually did. It's a super popular math problem. It's been around for 20 years, and there have been many solutions, but it's still very much an open subject of discussion. There is progress made every few years. So now, before I kind of go into the state of the arts, I'm going to express the needs we have for a consensus protocol in the safe network, and that's going to kind of explain why we ended up having to do our own. So one thing we need is for it to be asynchronous, because we're a network of computers run by people on a real network, and latency is entirely unpredictable. Like, for instance, you could have, I don't know, DDoS in some parts of the network, and you could have arbitrary long delays. If you try to say something like, I'm going to wait 1 minute and then do something, or I'm going to wait 1 hour and then do something, you're definitely not going to be able to function in a decentralized network in the real world. So we need something asynchronous. We need something scalable, because we're speaking about storing all the data in the world on all the computers in the world. So yeah, it has to be scalable. Basically, whatever is the best theoretically possible solution, that's what we need. It needs to work in a permissionless setting, and this has kind of two sides of the coin. One thing is anyone is running a vault, so anyone can do their own vault software that's trying to mess up the protocol. And another thing is everyone is running a vault, and not everyone has a super reliable data center where their node will never go offline, so nodes can just die at any point, rejoin, and we need to handle that as well. So that's dynamic membership, which is also needed for permissionless. We need for it to be open source, because our entire ethos is about having secure access for everyone, where everyone can review the code, everyone can know that we're not just doing something malicious on their hardware, they can contribute if they want to. So it's 100% part of our ethos that everything we do must be open source. And finally, if we can make it simple, it's better. And you could think it's just like me being, I don't know, a snobbish programmer who just accepts like the pure solution. But there is a very good argument for simple, which is security. If it's simple, anyone in the space can review it, and you can establish security. If it's complicated, maybe it takes 10 years before someone finds the flaw, and then you're in trouble. So now we know what we are targeting. We'll do together what we did in my team before going and designing our own, which is look at what's out there and if it could work for us. So blockchain we kind of ruled out pretty early because we know it won't scale since everyone has to store all the data. That wouldn't scale at the scale of storing all the data on the internet, or even all the data in a section of the internet. It's just too much. And also it's not asynchronous, which is another problem, but it wouldn't even be the biggest problem compared to how not scalable it is. Now there is a cool algorithm that came out in 2016 called Hashgraph. Maybe you've heard of it. It's gossip based, so it allows very efficient, permissionless consensus. It's pretty simple. It's almost asynchronous. They claim it's asynchronous, but they're a little bit full of it. But the main problem with this is that it's not open source. They've patented it, so if we wanted to use hashgraph to power our consensus, we'd need to, say, take the binary from them, maybe pay them royalties. But it's not so much that we don't want to pay royalties, although that's a problem. It's mostly that we wouldn't want to inflict a binary blob on our users. That's completely against what we're standing for. So hashgraph was never an option either. But now if you go into open source stuff, there is another cool one from 2016 called Badger Bft. And it almost ticks all the boxes. It's a bit complex because they use stuff like distributed signatures, which, okay, it's slightly complicated math. That wouldn't be a deal breaker. The main problem is that they rely on a common coin, which means that you can have asynchronous or permissionless, but not both at the same time. So in a static network, it's 100% asynchronous in theory, which is actually better than almost any other protocol out there, at least in this kind of speed class. But when nodes join and leave the network, there must be a synchronous step to share the secret to participate in the common coin. So basically, you can't have both asynchronous and permissionless, and we need both. Then this one came out actually the same week as PARSEC, so we looked at it just in case, like we could just ditch our last few months of effort. But it's actually a pretty fun, pretty cool protocol, but it's not asynchronous, called Avalanche. Except for that it's a really nice ID. It's got a bit in common with us, but it's got a different core ID, which is pretty interesting as well. So altogether, like, we ended up looking at all these protocols, and we became more and more convinced that we had to build our own. So that's why PARSEC happened, and now we are going to explain a little bit what it is. Okay, so spoiler alert, I'm going to give you the features before I go into how we obtain them. So before I go into the features, I'll just give you the general approach. So as I was saying with routing, we try to say represent something as an int, then solve a trivial problem. And with PARSEC, it's a little bit the same thing. We've got a complex math problem, and what we want is to reduce it to either a trivial problem or a solved problem or a formulated problem that's a bit simpler. And then by doing this, you can end up actually solving the problem if you do it enough. So yeah, spoiler alert, the features we got are asynchronous-ish. So every step of the protocol is 100% asynchronous by the theoretical definition of asynchronous, but one little step. And that little step we think is sufficiently asynchronous for covering the needs for an internet-type network with latency. The theoretical definition of asynchronous means that your enemy could control the time it takes for every message to be transmitted. And with us, if the enemy had that power, then they could delay the consensus for an arbitrarily long time. So that means that step, which is the concrete coin step, is not theoretically asynchronous, although we think it's good enough in practice. And also because it's a small subsection of the entire thing, once we are done coding what we've already formulated in terms of math, we're going to come back to it and try to make it completely asynchronous, because it's really shitty to have an asterisk on this slide.
Can I ask a question? What's Bitcoin? Is that asynchronous?
It's not asynchronous at all. It's not even, I think they're not even weakly synchronous, which is the next. We're a bit better than weakly synchronous. I think I shouldn't commit too much because we're a bit shady on this. We got called out by Vlad Zamfir from Ethereum for being a bit shady in this aspect. But well, you could say it's a little bit of a mathematical detail for purists, but we will definitely try to iron this out. Yeah, so Bitcoin is not asynchronous.
Is that because of the blockchain itself ordering things into a sequence of events? Is that why it's not asynchronous? I can prove you easily it's not asynchronous. If I'm the adversary and I'm mining, I can delay everyone else for long enough for me to find the next block. And because I have control on the duration, it's not asynchronous. And it's not even
what's the next one? Weakly synchronous, because I could pick a delay and then delay everyone by that fixed delay and do the same thing.
How does a minor delay everybody else?
No, you can't. It's a theoretical thing. The definition of asynchronous is the adversary can control the timing of everything that happens in the network.
Oh, I see. Okay.
So it's a theoretical property of the algorithm. Okay, we are scalable. We are as efficient as communication can be while staying resilient to Byzantine behavior, to malicious behavior. So we are basically as efficient as possible. And we are part of a few algorithms. By the way, I showed you like 4 existing algorithms for consensus. I showed you the 4 best ones out there. And so we're in the same class as these guys for scalability. Well, some of these, not blockchain. We're permissionless in all senses of the word. So we can have nodes dying, trying to hack the system, joining, we can do dynamic membership, and that's not giving up on asynchrony to the measure to which we are asynchronous. We are open source. The license is GPL v3 with linking exception. So it's not only open source, it's free software, but also it's not only open source in the license, it's open source in our attitude. We are really welcoming of input from everyone. We've already got a few commits, pull requests from outside, which we were very happy to see. We got feedback on the forum and in other channels like Twitter, and we are really welcoming of all the feedback and all the input that comes our way. And finally, it's simple. So in my humble estimation, it's about as simple as you can make a consensus protocol. Maybe someone can prove me wrong by doing something simpler, and that would be great, but I think it's basically almost as simple as can be, or as simple as I can see a solution at least. Like right now you see these features, you could think I'm taking a lot of the credit for it or on behalf of my team, but as I told you, what we're doing is trying to break down the problem into problems that are already solved. And all the simple, elegant, and efficient bits of our algorithm come from existing bits in the literature. So most of the credit comes from the paper from which we took inspiration, which are all listed at the end of our paper. So now I'm going to dive a little bit into how PARSEC works. And before I go into details, I'll be covering at a high level to give you an intuition of how everything works. So I'm in a section, and I'm a node. So a node means a computer. And computers are in sections, like we said, because routing shards, so everyone is responsible for a certain thing. A section is responsible for agreeing on things that happen in the section. One example of that is if a node requires to join the section, everyone already in the section must agree that this node is allowed to enter, and then this node can enter the section. So these things we kind of call, sometimes we call network events, sometimes they are called transaction in the consensus field. But basically things happen in the network, we've got nodes, and we need to agree that these things should happen, and we need to agree on which order things should happen. So say if I've got 2 candidates for entering the section, and maybe whoever enters first, because everything else is being equal, is going to end up being part of the people making the decisions. If one node thinks that, so let's give them names. Let's say if Alice thinks that Eric should be before Frank, but if Bob thinks that Frank should be before Eric, then you're going to end up disagreeing on who should make the decisions, and you're going to have a problem with keeping being in sync. So it's about agreeing that things should happen and agreeing in which order they should happen. So the way it's done, nodes communicate with each other through gossip. They gossip to each other. And they record all the gossip they ever received into a data structure that we call the gossip graph. It's a directed acyclic graph. What that means is that if you imagine I'm here, I'm receiving gossip from everyone, and I'm putting it in this data structure, it only goes up. I can never put an event back in the past of the data structure. That's what directed means. So I'm gathering a history of the communications that happened to me, at least during this consensus period. And I'm just stacking them on top of each other and keeping record of the links of who communicated to me and who they communicated to before, etc. And then when I communicate to someone else, I send them everything I know that they don't know about this graph structure. And at any time, everyone will have, or could have, and will have a different data structure for this. But what matters is that this data structure ends up converging for different nodes. So say the top of this graph could be more or less reliable because people can lie to you. But after a while, when you see that something has been seen by enough other people, then you can trust that it will spread. And that's because of how gossip works. I'll go a bit deeper into this in the next slide. So we built this data structure that we call the gossip graph. And then because this is eventually convergent, all we need is to look at the gossip graph and deduce an order in which things happened in the network. And this part is what PARSEC does. So it takes as an input a gossip graph or a section of a gossip graph, and as an output, it tells you this is the next thing that happened in the network in some order. And what you guarantee is that if you do this with your gossip graph and they do it with their gossip graph, they will end up with the same order. So when they ask which one is the next from the point where you are at right now, they'll get the same answer. That's consensus. So I spoke about gossip, and you could think it's some kind of vague, I don't know, like, yeah, gossip. It's actually a precise mathematical thing. And what it is it's the most efficient way to communicate in a resilient manner. So I'll explain two ways that don't have both these properties. One way that's to communicate that's inefficient, but that's resilient to malicious behavior, is you sit everyone around the table and everyone tells everyone else everything they know all the time. If you do this, if someone lies, they will be caught in their lie because you can see that everyone else disagrees with them. But the problem with this is that it's extremely expensive. In terms of computer science, if you're into this, it's order n squared, where n is the number of nodes. So this is not something that's sustainable for scaling. Then you can think of another way to communicate information in a decentralized network, which would be everyone sits around the table and everyone communicates to their neighbor what they know. And this would be very efficient. So say Ali speaks to Bob, Bob speaks to Carol, Carol speaks to Dave. So this would be efficient because you only need to communicate n times to propagate your message to n nodes, but it's absolutely not resilient because say if Bob decides to hide the message or replace the message by another message, then everything falls down. So gossip kind of combines being efficient and being resilient by using random. So you sit everyone around the table and everyone selects a random peer and tells them something at any time point. And it's not exactly obvious why, but there is a lot of research about this, and it turns out that the complexity of this is n log n, which is very good and which actually is proven to be optimal if you want to be resilient to nodes trying to lie or trying to be malicious and yet communicate your data. So it's not exactly ON because when you pick someone, it's not going to be the optimally best, like it's not going to happen to be the best person you could do for efficiency, but you do gain the resilient aspect by picking people randomly. So using gossip allows us to communicate data amongst ourselves in a section. But we still have two problems to solve. One is trusting, and one is agreeing on the order. For trusting, when we send a message to someone else, we have to sign it cryptographically, which means that we can be traced as the author of this message. And so if we start lying to people, they're going to be able to notice that we lied to them. So that's about signing. Now, I've been speaking of the gossip graph. Here is for you a simple illustration of a bit of a gossip graph. Right now we're looking at the leftmost one. So this is a record of the communications that happened in the network. Here you've got a network of 4 nodes called Alice, Bob, Carol, and Dave. Each circle represents a communication, except the bottom most ones, which represent just the initial event. So they all start with one circle, and then as they communicate with each other through gossip, they every time add a circle to their graph that represents who communicated to them. So, for instance, here, if you look at Alice, that may be from her point of view. After having created her initial event, she created a new event that recorded that Bob had informed her that Dave had spoken to Bob after Bob had spoken to Dave. So you see, Bob spoke to Dave, Dave came back to Bob, Bob recorded that in a gossip event, then Bob spoke to Alice, and Alice recorded that in a gossip event. So this is a gossip graph. If you want to understand PARSEC, everything is based on assigning meaning to these gossip events and figuring out a way to map this kind of like clutter of information into something ordered. One thing to note is that if things happen in the network, say Alice, Bob, Carol, and Dave can all embed information about what happens in the network in these gossip events. So they don't only communicate about what was communicated, but also about actual things that happen. And that's how you get something to order embedded in this gossip graph. Now I'm going to go through 2 very boring mathematical definitions that represent relationships between gossip events. They're a bit boring, but they're necessary, again, to assign a meaning to this graph. So the first one is about seeing. So we say that an event sees another gossip event if there is a path that's directed. So for instance, it only goes up between one and the other one. Another way you could see it is like, say, D4 sees B0. You could say that B0 is an ancestor of D4. But that's not sufficient. You need to be an ancestor of D4, and also there needs to be no fork in between. So I'll explain the concept of a fork. You can see here, everyone has a linear history of facts. And that's how it is if everyone is behaving properly. Now, if someone gives one truth to a node and another truth to another node, what you're going to see is this linear history is going to fork at some point. And so in the definition of an event seeing another event, if you can see a fork in the graph, then you do not see any event that's after that fork. So you unsee them in a way. So by having this definition of seeing, the differences that could occur between different nodes gossip graph get removed. So basically everyone would have the exact gossip graph if every node behaved and no one did forks. But by having this definition of seeing, even if you have a different gossip graph, when you see things in terms of nodes seeing other nodes, that's going to be the same between every node. Like exactly the same, not the same if everyone is honest. And then we've got an additional thing which is strongly seeing. By the way, when I say we didn't invent this. This is very common gossip stuff, but it's really the basis for algorithm. So strongly seeing means that, for instance here, A1 strongly sees B0. It means that A1 sees B0, and if you trace all the paths between B0 and A1, they happen to cover every node, 2/3 or more of the nodes. So here, for instance, it's 4 nodes, so 2/3 is 3, or over 2/3 is 3 nodes. So we also call over 2/3 of the nodes a supermajority because it's super common that we need it. The intuition behind needing a supermajority is that in Byzantine consensus, it's proven that if the enemy owns 1/3 or more of the nodes, you cannot get consensus. So the best you can do is be resilient to a third or less of the nodes. Sorry, to a third minus one or less of the nodes, to less than a third of the nodes. So in that case, by only requiring to see that a supermajority of nodes have seen this event, you will not stall if all the malicious nodes decide to stop communicating to you. But on another hand, it's proven that if you've seen that 2/3 of the nodes have seen the thing, it's past the point of no return in terms of gossip. So it will spread to all honest nodes. That's proven. There is a proof in our paper. It's already in other papers. So what it means is that when you start considering things you strongly see, no, with the seeing and the forks, you remove the difference between graphs because someone is lying to you. But no, you can also make sure that from this point on, even if they had forked, this version of the truth will spread regardless. So now I'm going to speak to you about interesting gossip events. We want to reach consensus on something. So as I told you, nodes are communicating, they're gossiping, and when an event happens, they record it in their gossip. What they do, we call that a vote. So for instance, say Frank wants to join the section with Alice, Bob, Carol, and Dave. So he goes and speaks to them, and like Dave says, okay, I vote that Frank wants to join the section. And in the safe network, in the things we need, we want to reach consensus that Frank should join and to reach consensus on the order. And we do it in that order. So first we want to reach consensus. So what we do is we take the first gossip event that can see a supermajority of nodes having the same votes. And we call this one interesting because we want to reach consensus on the order of interesting events. You could do it differently, and actually we're going to make PARSEC generic so that you can do it another way, and it's a bit more idiomatic in the world of consensus. So you could just consensus each vote and then bundle them into valid blocks or whatever. But that's what we do. So what we reach consensus on, we call the interesting events, or valid blocks is another word for them. So once we've identified these interesting events, and more specifically the older interesting event from each node, we define some other gossip events to have a special property, which is being observers. And these are events that can strongly see interesting events coming from a supermajority of the nodes. So because they can strongly see it, they know that it will propagate. You can't, so ideally you could say an observer is someone that can strongly see interesting events coming from all of the nodes, but then you would have the same problem with the reason why we use supermajorities, which is that if a third of the node stops speaking to you, you're stalling. So you lose the liveness property. So that's why we have to be content with the supermajority, but then we don't know at this stage that everyone else has the same supermajority. And that's why we need consensus on this. So to reach consensus on this, we do a vote amongst the observers, a virtual vote. So everyone can strongly see a supermajority, so they think that we should listen to these guys in the next decision. So their virtual vote for this, which is all stuff we assign, meanings we assign to the gossip graph after the fact. So we say they vote yes. And if there is people that don't strongly see the interesting event, then they vote no. And this yes or no is a binary number. So what we've done right now is, one, use gossip to make consensus efficient, and two, reduce the general complicated problem of Byzantine consensus to the simpler problem of binary Byzantine consensus. And this thing has a solution in the wild. There is a paper called Signature-Free Asynchronous Byzantine Consensus, with t lower than n divided by 3 and order of n squared messages, which solves the problem. Now, if you've been paying attention, I said n squared messages, and maybe that kind of smells bad, because I've claimed that we were n log n and efficient. And the point is that their algorithm is described over broadcast. But there is no reason why it couldn't map to gossip. And so what we've done is take this algorithm, very simply translate it to the world of gossip, and that's it, like the problem solved. So it's actually a very simple, very pretty algorithm. It's a few pages for the paper. It's already pretty when you look at it in terms of broadcast, but it becomes even prettier when you look at it in terms of gossip. And so that's it, that's PARSEC. Now there is a little extra detail, which is that this protocol, in addition to being broadcast-based, depends on a common coin. And when I was speaking about the alternatives, I told you some of them relied on a common coin, and that's not great because you can't have both asynchrony and permissionless. And now that's where we were pretty lucky, because a paper came out in 2018, about at the same time we were looking at the stuff, that explains how to remove the need from a common coin from algorithms in general and replace it by a weaker device called a concrete coin. And in that way, you can keep your permissionless and asynchrony assumptions. So basically, we were kind of at the right time to do this, because there was quite a bit of research from 2016 that moved the needle, and then this little thing from 2018 that for us really helped us close that last gap without having to do super nasty math, which you could kind of do, but then you would possibly lose some asynchrony or permissionless, which is what HBBFT did in 2016. So now that's it. And that's how we got the features we wanted, basically by simplifying the problems a little bit and then cherry-picking the best of the existing literature. So now we can go to the what's next section. And that's kind of three things. One is writing the code. So we've already written the consensus in terms of a static network. So that's a network where nodes are not joining and leaving. We've already written in the paper how to handle dynamic membership, and we've already spec'd how we will code that. So we are currently in the process of doing this. And right now, PARSEC is a standalone Rust library. So you can just take it, use it in your project, well, at least as soon as we're done making it handle dynamic membership. But then the next step after dynamic membership will be to integrate it in the routing layer and to have the safe network actually powered by PARSEC for consensus. Then we've got a few things in our minds for improving the paper. There have been some amazing feedback in the SAFE forum by a few members of the community, and some of it gave us ideas for, or like just said stuff that we could explain better, or so we're going to incorporate this feedback as well. And as you may have noticed, I'm not a big fan of our kind of asynchronous situation. So right now we're focusing on the implementation because it's blocking the next alpha version of the network. It's important to get that done. But when we've got a bit more time for goofing around, I'm hoping we'll get that sorted for good. And then since you're here, you must be kind of interested maybe in the safe network or in meetups or in both. So if you want a deeper dive into PARSEC, I'll be doing one with Bart, who's another member of my team who's also worked on PARSEC, and Doug will also be presenting the safe network at a high level. So we're just going to dive deeper into the stuff and explain a bit more how the binary consensus works as well, and how the concrete coin works, because right now I've just like, in the interest of time, I've just said that's what we used, but we'll dive a bit deeper. Then if you're into Rust, I'll give a speech at the next Rust London meetup, which is going to be sometime end of September. The date is not determined yet. This one is going to be about how when you implement something like PARSEC, it's not just the Rust language, it's everything around the language that helps you write production code. So it's targeted at a Rust audience. And then we've applied for MozFest, which is 26th, 28th of October. They haven't selected the speakers yet, so we don't know if we'll be speaking. But if we are, this one will be an entry-level introduction to the Safe Network, and kind of, it's a workshop, so it's like, come and put a website on the Safe Network and see how easy it is. So if you've got friends that are interested in the Safe Network but don't want to get deep into the weeds, this is a great one to get an introduction.
Is that London?
London, sorry. Yeah, the three of them are London. And that's it, thank you. Thanks for Cryptonomy for organizing all the event and doing all the hard work. Thanks to Rise for hosting us, it's this venue. And thanks for Made Safe. Thanks, Made Safe.